Hey there, welcome back to Short Text 331. Today we're going to talk about space-time determinant identities. This is a topic that is connected to our Toward Quantum Monte Carlo series, where we're building towards the finite temperature quantum Monte Carlo simulation. These space-time determinant identities are very interesting for reasons that will become clear towards the end of this video. But if you recall from last time, the last video, we talked about how there's this type of determinant that appears in the case of fermions when we're building our formalism towards the quantum Monte Carlo calculation. And for bosons, instead of the determinant of 1 plus this product, we get the determinant of 1 minus the product and then the inverse of that. So 1 over this determinant of 1 minus this product of matrices or exponentials of matrices. So here, to simplify notation from this point on in this video, we're going to take this e to the a sub k to be u sub k. So it doesn't really matter for us that these are exponentials. In this video, all that matters is that we have a sequence of operators here that are that we're taking the product of. So we're going to then call u sub k e to the ak, and so this whole product here, a to the a1 through e to the an, is going to be called u, where this u then is u1, u2, all the way through to un. And I will show you today that the determinant of 1 plus u in particular, so this for the case of fermions, and it's going to be the same proof, very similar for the case of bosons. I will show you that that determinant is equal to the determinant of this bigger matrix, where now you have ones on the diagonal. These are blocks, and then this sub-diagonal blocks are given by minus u1, minus u2, and so on and so forth. And so it's sort of a blown up version, this matrix, of this matrix here. So what will happen is that this matrix is of size space by space, or in other words, the size of this matrix is going to be given by the size of your single particle basis, whereas this one here is going to be the size of your space-time, or rather your spatial number of points, your single particle basis, times n. And this n is going to be associated with the discretization of time, of the temporal variable. And the reason for that is that, if you see here, we have u sub n, so we have minus signs all the way down here, but then there's a plus sign up here. So this looks like what we're doing here is that we're taking a derivative, and this looks like a discretized version of a derivative in this fictitious time direction, which ends up being an imaginary time direction in Monte Carlo calculations and quantum field theory formalism. And so this plus becomes an antiperiodic boundary condition for that time direction. For bosons, you have the determinant of 1 minus u. There's an inverse here in this expression that we discussed last time. That is not going to play a role here in this particular proof, in this particular video. But what we'll have for the bosonic case is that the determinant of 1 minus u, and remember this u is a product of all the u's, u1, u2 through un. So that determinant is equal to the determinant of this blown up matrix, where you have ones in blocks in the diagonal. The sub-diagonal is still minus u1, minus u2, and so on through minus u sub n minus 1. But you have a minus un up here. So there's no antiperiodic boundary condition. In this case, the boundary condition is periodic. So then, as I was saying before, the size of this matrix is space by space, meaning that if your spatial dimension is d, then L to the d is going to be assumed to be the size of your single particle basis, which is what happens if you put this field theory or this quantum system on a spatial lattice. So then you have as many degrees of freedom for each particle, or as many states for each particle as points on that lattice. And if that lattice is of dimension d and side L, then it's L to the d, where L, I'm assuming that L is the number of points in a given direction. And so, and that all directions get the same number of points, of course. And so we have then L to the d as the size of your single particle basis. That's the size of this matrix over here. And if this is space by space, then this is going to be space-time by space-time, because for each block here, we have a spatial extent, but we have n of these blocks. And so if n then is the size of our time, we're assigning that time interpretation, then the size of this matrix is space-time by space-time. Now, why would one want to deal with a bigger matrix rather than a smaller matrix? Well, there could be advantages to that in the formalism, it turns out, and there are, and it's useful to know these expressions in order to prove certain things, as I will show you towards the end of this video. So what's important here to note is that this matrix is completely dense, typically. So the same here, of course, this 1 plus u, this 1 minus u, they're both typically completely dense matrices, unless your system is not interacting, in which case this is going to be trivially a matrix that is diagonal in some single particle basis that you choose, typically your momentum basis. But on the right hand side here, these other blown up matrices are actually sparse. They're actually sparse matrices. You have the identity matrix here, you have zeros everywhere, and then you only have non-zeros in these individual temporal blocks, u1 through un. And so it's nice, sometimes it's useful to deal with these blocks on an individual basis rather than inside this big product of u where we have from u1 all the way to un. And so it's useful to know then these identities. Now, how do we prove those identities? These are completely different matrices, and I'm telling you here, I'm making this claim that this determinant of this massive matrix is equal to this, and similarly here. So how do we prove that? Well, we know that a determinant does not change if we add to a given row or to a given column a multiple of another row or a column. So let me give you an example of that property, even though you may already know it. Suppose we have this simple matrix now, 1, 2, 3, 4. And the determinant of this matrix is 4 minus 6, so it's minus 2. So we know that, and that's pretty simple. Now suppose we go ahead and take the first row and we subtract from the first row the second row. In other words, we take 1, 2, and we subtract 3 and 4. And so I do that here, and we leave the second row unchanged. So the top then becomes 1 minus 3, 2 minus 4, and then the bottom is unchanged. And so we have minus 2, 3, 4. If we take the determinant of this, we're going to get minus 2 times 4, that's minus 8, minus 3 times minus 2, so that gives us a plus 6, once again with minus 2. So you see it's the same result. We could do something else. We could go ahead and leave the bottom row, or rather leave the top row unchanged, and subtract twice the first row from the second row. Again, we're going to leave the top row unchanged, and we're going to subtract twice that row from the second row. And we could have done this with columns, by the way. I'm doing it with rows because it's easier right now. But if you do that, what I just said, then you get 1 and 2, that's unchanged. And then we have 3 and 4, and we subtract minus 2 and minus 4. So we subtract twice the top row from the second row. And what do we get? We get 1, 2, and then we get 1 from 3 minus 2, and 0 from 4 minus 4. What's the result of that from the determinant? The determinant of a double prime here is 0 minus 2. And so that's minus 2 again, as in the previous cases. So you see this perfectly fine. This works perfectly fine. And so then, like I was saying, we know that the determinant of a given matrix does not change if we add to a given row or a given column a multiple of another row or column. And this turns out to also work with matrix blocks. So if you have, for example, the determinant of this matrix that I made here simple on purpose. So 1A, 0, 1, where A is a block. Doesn't matter what size these blocks are, as long as they're all square. And so if we subtract the A times the bottom row from the top row, we get 1 minus 0, A minus A, which is going to be 0, and then the bottom we have 0, 1. And so the determinant of this matrix is the same as the determinant of this one. And so that's just 1, which of course we know here that the determinant of a upper triangular matrix is just the product of this of the elements on the diagonal. So that's known. But if you didn't know that, so then you know the properties of determinants and how you can change the matrix and keep the determinant the same, then you would do this operation, again, multiplying the second row, the second block row by A and subtracting from the first block, and you get the determinant of the identity is the same as the determinant of this matrix, which is just 1. So how do we apply this knowledge in our case? So in our case, we start with the fermionic case, and the bosonic case is going to be very similar, so I'm just going to do the fermionic case, and this is our matrix. So we have 1, a bunch of zeros, then u sub n, and then minus u1, and then 1 on the diagonal, and then u1, minus u1, minus u2, all the way to minus un minus 1 here at the bottom. So what do? We take this last row here, when we multiply it by u sub n on the right. We can multiply this by u sub n from the right. And so imagine doing that, and then what happens is that from that matrix, and you obtain this matrix if you take that row and you subtract it from the first row. So in other words, we're going to leave this row unchanged, but we're going to imagine that we multiply it on the right by u sub n, and we subtract it from the top row. And the goal of that is to eliminate this u sub n. Why is that? Because everything in this matrix looks really nice, except that this block up here is getting in the way of us calculating the determinant. Okay, so we're going to try to move this row, or this block here, all the way to the left. That's what we try to accomplish. And by this operation that I just described, multiplying by un on the right and subtracting from the top row, we eliminate this u sub n, but we end up with this now, un minus 1 un. Well, we can play the same game. We can take the one before last row and multiply by un minus 1 un on the right, and then we subtract it from the top row. And we continue to play this game, which is going to continue to move. It's going to continue to shift this top block all the way to the left up until you get here, where you can't go any further. And so you continue doing that. And once you do that, you see that you end up with this matrix. You end up with a matrix that is 0 everywhere on the upper triangle. And then on the diagonal, you get 1 plus this product that we called u above, u1, u2, all the way through un. We call this u above. And then 1s in the rest of the diagonal. And then the off diagonal below becomes minus u1, minus u2, and so on, which is unchanged from before. And we're not touching anything else down here. So all that is all the same. And so this tells us then that the determinant of this matrix over here is simply the determinant of this matrix, which turns out to be just the determinant of this guy up here, because there are ones on the diagonal after that. And so that determinant of this big matrix is just the determinant of 1 plus u1, u2, all the way through un. And so that proves the case for fermions. Then the proof for the bosonic case is identical. It's just that you have to keep track of this minus sign over here, and you end up concluding that the determinant of that matrix with the minus sign is the determinant of 1 minus u1, u2, all the way through un. So that is really how you go about proving this. Now, these identities have many uses, as I was saying at the beginning. Knowing that the space formulation is connected to a space-time formulation is useful to prove a lot of stuff. It's useful also to connect to relativistic quantum field theory. So in relativistic quantum field theory, it is the space-time formulation that is the most natural one. So in reality, one lands on the space-time formulation in that case, and there's no obvious simplification that would give you just space, because in relativistic QFT, space and time are on the same footing. Now, in non-relativistic many-body physics, which is what we've been doing, we land on the spatial formulation right away, and from there, as I was just proving in this video, one obtains something that looks like a space-time formulation. And so that's what connects to the relativistic quantum field theory formalism. And in my research, I have used actually these types of identities for other purposes, like simplifying entanglement calculations. And this is a paper that I wanted to show you because I'm very proud of it. It's a really nice paper I worked on in 2016 with one of my students, and it's called Entanglement, Noise, and the Cumulant Expansion. And we here in this paper, we used this type of identities to simplify the calculation of Rényi entropies of simple systems like the Hubbard model. And we showed that even though people thought that it was not possible to go to high order Rényi entropies, by using this type of identities and simplifying the calculation, turns out you can go to very high order. And here, to show us an example, we went to up to order 10 for Rényi entropies. We stopped there just because we wanted, but we could have gone to higher order as well. So that's all I have for you today. I encourage you to go check out this paper and send me questions if you have any. Other than that, I hope this was useful and instructive in some way. And if you do enjoy these videos, please consider liking and subscribing. And as always, if you're looking for a tutor in physics or math in English or in Spanish, you can contact me at shorttake331@gmail.com, or you can leave a comment in the comment section below and I'll get back to you. I'll see you next time.